Hello. Good morning. Yeah, can we just start now? Yes. Okay. So today, my topic is Uclamp sum aggregation. So this is exploring a different implementation of Uclamp in the scheduler. So a very quick introduction of what Uclamp does. So it's a scheduler hint. It's a performance hint. What you can do is basically there are two values, Uclamp min and Uclamp max. And these two values range from 0 to 1024, and 1024 being the highest. What you can do with Uclamp is, for example, in Android, when you scroll on the phone, you always have this first frame jank problem because with schedule tool and the pelt signal, the utilization takes time to ramp up. And when the utilization is still going up, the frequency, the OPP selection will be low. So you will have a couple of jank frames first. And only after a while does the pulse signal go up. Then you will have like a smooth experience. And giving it a Uclamp min value tells the scheduler, okay, I want to have this much performance even before you see the pulse signal going up. Another use case is, for example, an always running background task. If you don't give it any hint, it will inevitably drive the utilization to the maximum and will choose the highest OPP on the CPU. And sometimes we don't want this. Like, it's always running, yes, but it doesn't mean we want the maximum performance for that. We can give it a Uclamp max value to say, okay, just give me this performance, and you don't need to give me more. Okay, so a quick overview of the current implementation, which is max aggregation. So what this does, if you look at the diagram on the right, so you on the run queue, you have 4 different tasks, and on the left, you have all the Uclamp min values. On the right, you have all the Uclamp max values. So what max aggregation does is for all the tasks on the run queue, I pick the maximum value from all the Uclamp min, and I also pick the maximum value from all the Uclamp max. And I use this to drive the run queue frequency. For example, if let's say in the end you have a run queue Uclamp min of 400, run queue Uclamp max of 600, if in the end the CFS, not CFS, but the run queue utilization is only 200, then this will tell the run queue, please run at 400 because that's the minimum. And if the utilization is like 800, and then Uclamp max will tell the run queue, yeah, just run at 600. I don't need more than that. Yeah, there's also the Uclamp buckets implementation, which I won't go into too much detail. So basically, whenever you dequeue a task, you need to know the second highest value, because then you need to pick that value. And the bucket implementation, it approximates, like it keeps track of the value. It's an approximation, but it works. And yeah, that's how you know when you dequeue a task, what's the next highest value. When I'm using this, when I'm testing this implementation mostly in Android workloads, I would say there are a couple of limitations of this implementation. The first is Uclamp max always leads to very strange behavior. Although that's not, I would say in the end, I'd probably say something about Uclamp max, but I think Uclamp max is quite tricky to handle in general, like regardless of how we implement Uclamp, that's actually quite tricky. So I think recently there are also in the mailing list, there are a couple of CPU freak patches needed for Uclamp for max aggregation to work better. It's a bit complex. And actually, I would say the first 3 problems are, I would say, not big problem. My problem with max aggregation is actually the last one, which is if you have more than one task on the same run queue, then it's kind of unpredictable, like how much performance you can get from Uclamp min and Uclamp max. And I will go into detail and elaborate on this. For example, let's say there is a render thread, and its only job is to render frames on the phone. Let's say this may not be a good example. Let's say you have two, like your phone for some reason has two screens, and there are two separate threads rendering on the two displays. And assume these two threads somehow end up on the same CPU. Of course, this might be questionable to start with, but let's just assume that. So I use Uclamp min of 200 to avoid the first frame jank problem. And when you are starting this thread, the utilization is only 100, which means if these two threads run on their own, their utilization says 100, but actually the Uclamp min tells the CPU to run at 200. Okay, that's all good. But what happens if somehow these two threads end up on the same CPU? Of course, I'm making it much simpler because in schedule, there's also the 20% margin. So if you say 100 utilization, actually it will go to 120. But let's just make it things simpler. If these two threads end up on the same CPU, so each utilization is 100. So the total utilization is 200. So the CPU is already running at 200. So if I say Uclamp min, like each thread is saying Uclamp min of 200, with max aggregation, the Uclamp min is still run queue Uclamp min is still 200, which gives you the slightly strange situation that you are not boosting the run queue at all. Which means if somehow you have two displays and somehow the two render threads end up on the same CPU, you might still have the first frame jank problem. And maybe the final Uclamp min value should be higher than this. It should not be like 200, and then we just pick 200, and the CPU is already running at 200. Maybe it should be slightly higher than that. Yeah, I had this problem when I was mostly testing Android workloads, and I'm wondering like if there's anything an alternative implementation for this.
So Uclamp min is just to ensure you that you will run fast enough to execute what you have to be done. What you are trying to explain there, it's another thing. It's a scheduling decision which one should run first. It's two different things. And I would say at the opposite, if you ask for 512, I mean, that doesn't mean that you should run at the highest frequency. I mean, if you're using 512 for each CPU, that will not give you any benefit. So that's really, you have to take care between how fast I want to execute myself and where should I be placed or to meet my deadline constraint, which is two different things.
I know. I mean, but with some aggregation, you can have like, it doesn't make, in my test, of course, it doesn't make test placement worse. And I'm just assuming, like in some in manual tests, things always, like with Uclamp min, they can end up on the same CPU. You may say, oh, maybe we should improve Uclamp max aggregation to make sure this doesn't happen in the first place. But I would say, if this happens, yeah, with some aggregation, you can still work. Or sometimes you have like CPU pinning, they have to be placed on those CPUs. They have to end up on the same CPU.
Yeah.
And with that, some aggregation still works. I mean, yeah, what I'm saying is that, yeah, this still works with some aggregation.
For me, that makes sense. The mean is really that because your utilization doesn't reflect how fast as you would execute your instruction. So that's it. You want to execute twice faster, and you will run twice faster than if you were without any Uclamp.
I guess the point, one point I want to make as well is that the reason why we use Uclamp in most cases is because you have tasks that are in a pipeline, right? So you want to make sure that you don't just look at the utilization of the task to select the OPP at which is run, so that you can produce the data fast enough so that it can be picked up by the next pick. So in the case that we have here, when both tasks are co-scheduled, the poor task that's going to come second is going to be late if you don't, because this would be equivalent as, you know, if you were running the first task, the second task alone on the CPU without Uclamp, you would finish at the same time. So
yeah.
So max aggregation makes it pretty hard. When there's co-scheduling, it's basically impossible to make sure that your tasks are going to be on time. You have to overcommit your Uclamp values. You have to put just to deal with the co-scheduling case.
Yeah, but then it's a scheduling decision to know which one you want to run first.
Sure, but
if you put as I mentioned, if you put 512, you will always run at max frequency without any good result. So for me, that's really how fast you should run. It's not, you're not provisioning some bandwidth.
So, well, no, you're not provisioning some bandwidth. You're just trying to say, I want to make sure that this task is going to finish its execution fast enough so that the next thing in the pipeline can use it.
That's probably the difference. In this case, you should have a deadline for your task, which is different.
Well, okay. Using deadline for this type of stuff is just
I mean not skate deadline, but what you are trying to explain. You want a deadline. I want my task to finish before that, which is different from this.
Yeah. So
you mix two things.
Okay, but this is a task placement problem that you are trying to solve by ramping up the frequency, which is kind of fun because the tasks shouldn't be placed this way in the first place. In this case, this is the task placement problem. It cannot be solved by ramping up the frequency.
I agree. But you can always end. It's just that you have to take care about how fast I want to run, and if I have a hard deadline. Hard deadline, not from a deadline scheduler point of view, but what you're seeing in this case is that I want to finish in a millisecond, whatever is running beside me, which is a different thing. Yeah, but that's
it's useless. Nobody wants that. That's semantic. I can't see a reason for it. I mean, why would you ask to run at a specific frequency if you don't know how many other tasks you're sharing the CPU with? I mean, that doesn't give you anything.
That just give you
with max aggregation, you can ask for a min clamp of 200, but you might be sharing it with 1,000 tasks and you get almost zero throughput.
Yeah, but that doesn't mean you will use the 200 at the point. I mean, when you're asking for 200, you will not use this 200. That's two different things.
You might or might not. You don't know. Do you?
No, I mean, because your utilization, based on your utilization, it's just that you want to run faster than your utilization is reflecting to the system.
You need to add the things up, otherwise it doesn't make any sense because you're not guaranteed your throughput. So Uclamp with the current semantics is basically you want the CPU or you want the core selection you choose to run at a specific performance level, but you sort of give away a lot of your throughput guarantees, which is useless.
That will not provide you anything because at the end you can have a system, a CPU that will remain almost idle just to provide enough bandwidth. As I explained, take 512 there. And if you run 100 microseconds, then you will not have any other task because you're provisioning all the CPU for just 100 microseconds.
Dat is Vincent.
That's the point.
Yeah, I would say.
So you will put everything out, and that's not what you want. What you're describing is different. You have a deadline. You want to finish your execution. And Uclamp will never be able to provide such information.
No, but then I think we should just remove it because it has no practical use.
I think it has.
For what?
If you have a really short things, I mean, it can be used alone. That just ensure you a minimum bound execution performance level. That's the point.
Yeah, for the amount of time you're getting on the CPU, which you cannot control.
Yeah, but then you have the goal is to have some other hint to make sure that you will run first.
What's
there is
that
two
hint?
things. that the discussion we were discussing about the latency.
Okay,
were
so it's
discussing-
something that doesn't exist. So we have something in the kernel that's useless as it is, and we don't have anything to.
I
make
don't
it
think it's
useful.
useless. It's not enough probably for your use case. They're two different things. There is
Okay,
two things.
so that's what we're discussing here.
Yeah.
To make it into something that can actually be used for real use cases.
Yeah, but for me, the sum aggregation is not the right answer. Provide a deadline, provide maybe a period, provide a runtime, and you will have everything to make sure that you will.
Then you're asking for skip deadline that you're never going to.
No,
do.
we can use that even for the CFS or the EVDF, because then you're able to provide the bandwidth, how fast you want to run. And then when we are placing tasks, you're able to decide if you can put that on the CPU, because it will run first.
I don't believe you can use that in practice, because quite often you don't want to express a deadline per task. It's often a whole pipeline of tasks, and you actually have a combined deadline for all of them. So if you really want to solve that problem, we need to have task graphs in the scheduler.
You need to have what? Sorry,
You need to have the task graphs to make the right scheduling decisions. That's the only way if you want to plan everything.
Yeah, but there you. I think it's just the wrong things to do that, because it's just that a way to hide another problem. You're trying to anticipate some task placement in something which is not about task placement.
I'm trying to create an interface where the user can ask for a certain throughput for a task when it runs.
Yes.
Which we don't have today, which is a big problem for real use cases.
But that doesn't mean that this solution is the right one, because you will not cover all the cake. And I have this use case, 512. If you have a task that runs 100 microseconds every 10 milliseconds, so you ask for 512, you put two tasks, your CPU is become overutilized.
So is Uclamp taken into account when in the wake up path? Where yes. Okay, so this works because it won't place too many tasks with high Uclamp max on one CPU, right? So it works this way.
Yeah.
So it kind of causes them to get their own CPUs. And that helps.
Yeah.
But call scheduling is a problem. But then if you use like sufficient Uclamp max to get over the small core capacity, for example, then you can influence the distribution of tasks this way.
Yes. Yeah.
So
but so you said your use cases, you have like 100 microsecond task that runs every whatever, and that's precisely what case it's trying to filter out, or was trying to filter out recently, these short tasks, because it doesn't make sense to switch frequency that fast for him. If you remember his patch set. So
okay, so where do you want to go? I'm not sure.
Then I don't understand, because what's the use case of Uclamp then? Because then now we have like three different.
I can take 1 millisecond over 10 milliseconds if you want. I mean, that's just the same thing. It's just that my point is that.
No, I'm arguing about 100 microseconds, not the 10 milliseconds.
Okay, let's say 1 millisecond every 10 milliseconds, the program is the same. That's exactly the same.
I don't understand what the problem is. If you're saying that you want 512 min clamp for a task that is really small, it's presumably because you want that to run really fast because it's got to deliver some data to another task, right? And so if that ends up being co-scheduled with another task of the same nature, you probably want to go to 1024.
Yeah, but then if you have a subtask that will come, they will say, okay, I'm overutilized because I
Well, yeah.
But that's not the case.
Yes, it is, because you're going to be late.
No, it's not.
Actually, in this case,
because the third one can just wait for 2 milliseconds to start to run, so you can co-schedule that. It's really a matter of the deadline that makes the difference.
actually, in the RFC, this case won't be overutilized, but that's another detail. So if you have a short task, you can place two. And only like in the RFC implementation, we'll first check if the Uclamp values, they overutilize. If the answer is yes, then it checks the real utilization. If both answer is yes, then it's actually overutilized.
Yeah,
But
that's the right
I'm still
interpretation.
thinking about that.
Sorry?
I'm still thinking about whether like
Yeah, but in this case, how do you make sure that the one that you will add will not preempt these two one? I mean, we are back to this situation. It's for me, it's not enough for what.
I'm not saying it's enough. I'm saying today, if you have Uclamp, you just can't use it. Like the only reason we introduced Uclamp in the first place is because the scheduler doesn't understand dependencies between tasks and pipeline. It just assumes that different tasks running in different CPUs are independent from each other, right? The way schedule does a max of the request for all the CPUs in the frequency domain to select the frequency of that domain is basically saying the CPUs are independent, which they are not. And so we put things into groups where a bunch of tasks in the pipeline, and we say, oh, this group of tasks needs to run that fast to make sure that, well, on doesn't matter on which CPU they are, we're going to be running fast enough. And without that, we would just break the fundamental principle of Uclamp. So I think, yeah, if you don't have that, co-scheduling with Uclamp makes it pretty much useless.
Do something different if you had an interface to describe the dependency directly instead of using something.
Yeah, if we had the graph of tasks, we might just be able to remove Uclamp, to be honest.
So maybe the question is, do we?
Well, that's a hard problem.
That, yeah, which is bigger than this, maybe in the long run. Like, well, because this discussion about pipelines, I think we've been having those for years. So,
yeah, to be honest, I'm less drastic than that. I'm just saying, like, in situations, some aggregation might end up performing better. I'm not sure if I want to completely remove max aggregation. It's not like I would say it's still. I will show you some performance numbers. Like the performance numbers are not that bad, but just in certain cases, some aggregation performs better. And I think, yeah, my only, like, if you just see from another point of view, if you end up in that situation, then Uclamp min doesn't do anything. Like that to me is, yeah, something I just don't think is right. Like in that case, in the case on the right, Uclamp min still should do something. Like intuitively, let's say I'm using Uclamp for the first time in my life. If I end up like this, I think, yeah, Uclamp min should still do something. But in reality, it doesn't do. It doesn't boost the frequency. So I think, yeah, I mean, intuitively, this might seem the case for other users. So yeah, maybe we should explore alternative implementation. I'm not saying an alternative implementation will completely solve the problem, but just let's look at it and see how it does. Yeah, then I'll just skip this. Yeah, I will make things very like to the extreme. What max aggregation does is that as long as the task is running at the frequency, the Uclamp part won't complain. So I could end up with an infinite number of tasks on the same CPU, and each task is Uclamp min 100, Uclamp max 200, and the CPU capacity is 300, and this CPU is running at 200. And the interesting thing is, this will not trigger overutilization. So I think in reality, you will never end up in a situation like this. But let's just say that there's a like theoretical hypothetical situation. And this is, I think, will show you that maybe there's something wrong. Yeah, because this works. This won't trigger overutilization. Let's see if an alternative implementation solves the problem. I'm going to summarize all the whole patch series in just this single slide. So if you have Uclamp min, Uclamp max, you first clamp that, and then calculate the difference between util average and the clamped utilization. You get a util average bias. You then sum up all the bias, and then you get an RQ bias. Yeah, if I have to summarize everything in a single slide, that's it. Okay. That sounds simple enough. From a overview, it is simple. And how does it work in practice? So when you enqueue a task, add the bias to the RQ bias. When you dequeue task, just remove the bias. When you do update load average, this one is interesting. You have to make sure you get the new bias, of course, but you have to make sure the sum of all the biases they stay in sync all the time. So every time you update the bias, you also need to update the RQ total. Actually, yeah, that's pretty much everything that is true in sum aggregation. And I give you an example. So there are two tasks. The total bias 150. So you would actually raise the frequency by 150. And then there is an update load average. So the second task now goes from 100 to 300. Now that falls inside Uclamp min and Uclamp max. So the bias is now 0. And then after that, this update, then you get the new bias, which is only 50. Because second task is already like getting enough performance it gets. So yeah, you won't bias that much in the RQ total. Okay. And yeah, that's basically it. Actually, there are many details in there. Some corner cases need to be addressed. In its current version, yeah, it's actually way less code than max aggregation. And maybe like there are still a couple of problems in max aggregation. Maybe if we want to solve those problems, maybe the gap, the code, amount of code will be like the diff will be even larger. Yeah, that's actually everything. The code, like I'm simplifying a couple of things, but yeah, to summarize, that's basically it. Yeah, there's some discussions on LKML about, does this change the definition of Uclamp? I thought about this, and then I think it actually does in a way. So instead of providing you with some frequency, target CPU frequency, this gives you like frequency multiplied by some amount of time. For example, if you have a task, like let's say task A is running alone, and Uclamp min of 200, it will give you like, it will run at some frequency, run for some period of time. If there's another task, task B, it will make sure that the frequency times the amount of time, execution time is still 200. So yeah, because you are competing with another task B, you're only getting half the CPU time. You actually get twice the frequency in this scenario, which means, yeah, that's, yeah, that this is something, I would say this is something, I wouldn't say it's perfect, but I would say it's more meaningful than just running out of frequency, because with just the frequency, without knowing how much time it will run, there's really not much you can guarantee. But if we think of it like this, like some sort of bandwidth hint, yeah, it gives you a stronger, like it's a stronger hint. Yeah, that's what I think about this, how I define this new aggregation implementation. Okay, let's move on to some testing and the benchmarks. So the above is max aggregation, the below is sum aggregation. So you run 4 tasks, each with a Uclamp max that is lower than the max capacity of the small CPU. The little CPU is from CPU 0 to 3. These 4 are little CPUs. CPU 4 and 5, they are big CPUs. Yeah, I mean, I would say both do a decent job. Although in the max aggregation scenario, this doesn't happen all the time. It sometimes happens, but I just I took the one where the problem happened to just make sum aggregation look really good. So when sometimes, because you can say that max aggregation is targeting some level of frequency. If you end up with 2 tasks running on the same CPU, Uclamp still holds because it's still running at the same frequency. It's just you only get half the CPU time. Yeah, that's sometimes that's the problem I see with max. That's also why I want to explore sum aggregation. With sum aggregation, yeah, because everything, like BIOSes are summed together, you won't have this problem. Because yeah, if you have too many tasks, in the end, the sum will explode. So the scheduler will know, oh, it's really time to schedule on another CPU. In sum aggregation, yeah, you have the balanced task placement. Yeah, the next one is if I give a Uclamp min that is larger than the little CPU capacity, this is a hint that tasks should be run on big CPU. Both achieve this job perfectly, so that's good. There's a very nasty problem with max aggregation, which is because you take the max value of Uclamp min or Uclamp max, you end up in a situation where, let's say you only have task A, which is an always running task, capped at utilization 300. And there's a small task that wakes up, which doesn't have any Uclamp value. So default Uclamp max is 1024. The moment that task wakes up, the RQ Uclamp max value will go from 300 to 1024. Because the task A is an always running task, which has utilization pelt value of 1004. This means every time the small task wakes up, you have this uncapping effect. Then the total run queue utilization would go from 300 to max. And then that small task goes to sleep. I'm also like, this is artificial workload. I try to make something that can look better. In fact, you won't end up in a super nasty situation like this. So the small task wakes up, goes to sleep, wakes up, goes to sleep. And with some aggregation, you will end up like this. You will go from, change frequently, very fast between two OPPs. In some aggregation, because you just sum things up, actually, I would say you still have this uncapping effect. But actually, the math is quite tricky here. I would say that you uncap in a way that you won't uncap to the max. You just uncap enough to make sure the small task has enough bandwidth to run. Actually, this won't make sense without going code. But with at least with some aggregation, because everything is summed together, we are not just taking the max value from all the Uclamp and Uclamp max. It will make sure when you uncap, you only uncap a short amount, a very small amount, so that you will end up like the red line is the utilization after considering Uclamp. So that's that, and you will see in the CPU frequency, it would just stay the same. And of course, if I really have to be nasty here, I could just because there's still uncapping effect, I could place the OPP just right behind, right in the middle, so that you still see the bump. But normally you won't see this. You will also see the fast frequency.
So, but just in this case,
okay.
So your system is fully busy from a utilization point of view.
Yeah.
You're not running to the highest frequency, but you don't know when your small task will really run. So you might end up waiting quite a long time because you're not running at the highest frequency. So you're breaking the fairness of this small task that doesn't ask for anything else. That
but that's what pelt does, right? If I run this task, I see the pelt value. I then know how to drive the
CPU. But right now the pelt value say the CPU is fully used. So run at highest frequency to provide enough bandwidth for everybody.
No, with max aggregation, yes, but with some aggregation that doesn't, like the pelt value, you will see the pelt value, but you also
taking into account some or max aggregation. In this case, your CPU is always used. You're capping the frequency when you have your main task running on, and then you have some task waking up shortly.
Yes.
And you will slow down the execution of this. I mean, if without any Uclamp, this small task would have run at highest frequency. So,
why? Yeah.
No, but I mean, he has to share that the point. He has to share the CPU.
Yeah. So I only raise it.
No, because if you have to wait, we are back to the situation. If your task is not scheduled right now, it will be runnable, waiting for the other one to run, but the other one will not run at full speed. So you're slowing down everything.
But that's not what we do in CFS. CFS is about throughput, isn't it? It's getting the throughput it needs. I mean,
no, it's getting the share of the CPU, but then you're providing a lower share because you're capping the frequency.
But this task is a small task anyway. So if a task runs alone, you won't give it much CPU frequency anyway.
Yeah, but when it's alone, it's fine. It's just that if you look there, it will not have the share that he was expecting, or at least it will run slower than it was expected.
No, I don't think so. It's running faster because it happens to be co-scheduled with that task.
No, because you don't know. You might have to wait before running.
Yeah, but it's the same if you co-schedule with an unclamp task.
Yeah, that's the same if you don't have Uclamp anyway.
So there's no difference in the service it's getting.
I'm pretty sure that there is.
Yeah, but no.
And again, because there is also the recent discussion about filtering, so we want to filter this small task anyway. So
the above scenario makes it pretty useless too.
So we actually did some experiment with Uclamp Max, and that top scenario is the main reason we just decided not to use it, because like the thing is, if you put your background group, for example, you put a Uclamp Max on your background group, just because you happen to put the fact that the CPU is fully utilized and there's no idle time is an artifact of Uclamp to start with. It's just because you blow out the frequency below what you really need. And that basically bloats. If there was no Uclamp Max, there would be idle time, and so the utilization.
You don't.
Yeah, well, in our use cases, that was the case, and so just by lowering the Uclamp Max, that's the point of Uclamp Max, right? Uclamp Max will remove your idle time. Otherwise, there's no point in having Uclamp Max. Well,
no, you might. It's just that you know that.
You
don't always want to remove the idle time. Just that you don't need.
Well, by definition, if
that's the consequence, but that's not the
well,
first goal.
No, it's not the first goal. But so you want to run slower, so that removes the idle time. But as a consequence of that, and that because of the Pelt machinery, when there's no idle time, we just blow the utilization. And then all of a sudden, as soon as you have one small task that's unrelated to that, some kernel thread that wakes up, just boom, the frequency goes up to the roof. And then that's just completely, that is actually worse than not having Uclamp Max to start with, just because you have these massive spikes in frequency going all the way up to max. And you're stuck with that for like 10 milliseconds.
That's the only way to ensure the fairness. That's why I'm saying that.
I don't think so.
Maybe, Quentin, wasn't it Google who introduced some aggregation in one of the products? The Max problem, right?
So there's lots of different people do different things, but it's common to have downstream implementations of Uclamp that do some aggregation. Yeah.
Exactly. This is maybe, and that's why you have all the experience with your products on this issue.
This is one of the reasons that people are doing some aggregation. So that.
So I mean, from Google as well. But this is what I don't understand. Yeah, so I want to say that case from Google is saying exactly the opposite. So I don't know. I don't know where is the truth. My point is that you're trying to hide some problem, and you need what you're trying to solve can't be solved with Uclamp Max min or max aggregation or some aggregation or whatever. In your case, it's just that you want to ensure some deadline for some tasks, and you want to ensure some bandwidth for others. And that's not the right, for me, that's not the right way to do. You will probably fix some of your case, but you will introduce more. That's why.
I think Uclamp is a practical solution to many problems if it was doing the right thing. But it's just, it's just a bit of a shame that the main user of this have to make massive change. Android is the main user of this stuff. And we just have to make massive changes to it to make it work. It's a bit of a shame, honestly.
Yeah. If we decide this is the useful interface, that's one thing. Because if there are better interfaces, maybe we should try to work with that. But if this is a user interface, maybe we could make it configurable, so it actually could. From what I get from this discussion is that there are different use cases, and each use case might need a different type of aggregation or so. But again, not sure if we are making the right choice on making this more complicated, if it's not the best interface we can come up with, but I don't know. Yeah.
I would argue that this is a simplification. Yeah.
Simplification of what?
The code, at least. This is significantly smaller.
Simple.
Simpler implementation.
But the majority of the code reduction is due to the that we get rid of the buckets, right? And I think Case is trying exactly the same, where he wants to switch the Uclamp values when the task schedules. And I'm not sure if this is possible. So that's why this is a solution. And code reduction is important, right? Like, because it's getting too big, this whole thing. Awesome.
There is another point, is that's already what I mentioned to you, Patch. I don't like you manipulating the Pelt like you're doing.
I'm not. I don't think so.
So you're not doing some decay outside of the pelt signal?
No, that's
Even
V.
with the BAs?
Yeah, that's
prefer?
V. Yeah, that's. I mean, I
Yeah,
can show
no,
you.
you have exported some function in order to
Oh,
decay since.
That's V1. Yeah, that's V1. Now there's V3. Everything like becomes
So
so hot.
you're not doing any pelt.
No, I just don't need to. I would say for things to work better with Uclamp Max, I did some trick there. Although I'm not like, because max aggregation, there is a interesting problem. If you only have a Uclamp Max task, the moment you DQ, the Uclamp Max is no longer there. And then you will shoot up to the maximum. To solve this problem, max aggregation does this thing where if the last task is a Uclamp Max task, if it DQs, the Uclamp Max stays there. What I'm doing, actually with some aggregation, you don't even need to do this. You probably just see slightly higher power consumption, but you don't need to do this. But if you really want to avoid the frequency spike, what I do is that if there is a Uclamp Max, it makes sure the negative offset is slowly decaying. And it decays just like what the task is decaying, what that task is decaying. So that's I put it optional patch because I know you don't like it. So that patch is optional. Without that patch, you will see some slightly higher power consumption, but still works. SAM averaging still works. Yeah, and that's a big change from the previous revision. The previous revision is where the bias always go through pelt as well. So if you have a positive bias, even if a short task, if the task DQs, the positive bias will slowly go to 0. And that's kind of unnecessary. And in this revision, things become much simpler, like that doesn't happen anymore. Yeah, I'm sure like if we go to the past series and if you look at the detail, I'm sure we will also debate here and there. But yeah, I'm giving just how it works today. Yeah, this is that. And also, yeah, the next slide, I like what was on the presentation yesterday, invalidated slide. So basically, at the moment, so let's say there are 8 tasks. They are all with Uclamp Max. The 4 tasks are run from CPU 0 to 3. There are another 4 tasks running on the big CPUs 4 and 5. These are pinned to the small cluster and the big cluster. And at some point, I unpin those tasks on the big CPU. And what should happen if EAS does its job is that it should know there's a Uclamp maximum, and it should understand that it's okay to put 8 tasks on all the small CPUs. Yeah, for max aggregation, that's always the problem that it runs at some frequency. So it won't complain if you have like 5 tasks on CPU 0 and 1 each on CPU 1 and 3. But with sum, because everything is summed up, so that sum gives you like a balance of task placement. But I think last one yesterday, he also proposed something, and it's no longer that bad anymore. So yeah, this slide might not be valid.
And in this case, what's happened? So I assume that you put in your case, you put the number of tasks such that the sum aggregation is not higher than the maximum compute capacity. What happens if you put one more task in this case? One of the sum aggregation will go above the CPU capacity.
Yeah, and then it will run on the big CPU.
Okay. Oh yeah, and so I would say in the trigger case where you have so big, medium, and small, you set your max aggregation to be, I would say, on the medium, which means that normally the little core is not fitting.
Yes.
So you're adding, and once the sum aggregation of this mid core and the big, when both mid and big core are fully used, and you add one more task with the sum aggregation, the sum aggregation will be above the CPU capacity.
Yes, and it will push things to the big CPU.
And once the CPU is fully used, what's happened?
You don't have you then have actual your overutilization.
Okay, but then in this case you are breaking everything.
I mean that's what I'm talking about with the infinite task problem. That has to happen at some point, right? If you start piling up tasks, overutilization, and something has to happen at some point when you add more and more tasks. I would say like adding an infinite number of tasks and Uclamp still doesn't complain. That's definitely, I don't think that's correct. And it should complain at some point. And I think, yeah, this is just complaining at some point. I mean, just to answer your question, direct, I think that's in my mind, that's the right thing to do. I'm sure that people might disagree, but I think in my mind, that's the right thing to do. Even if you have Uclamp max, the moment you reach some number of tasks, things should explode. And with some real world benchmark, I'll quickly go through this. So speedometer is test benchmark. It's test browser. It tests the browser performance. So with max aggregation score, CPU power, with some aggregation, they're slightly different because some aggregation doesn't circumvent the 20% threshold. So for values to be exactly the same, you have to use some aggregation with only 80% of the Uclamp value. So with that, you have better score. Of course, CPU power consumption is higher, but then I reduce the Uclamp values such that the score is can match max aggregation. It's still higher, but then at that point, then you actually consume less power, and then the total energy is almost 2% lower. And with UI bench, like in the latest Android image I got, it's getting tricky because max aggregation already gets really, really good scores. And CPU power is already low enough. This is not all the benchmarks. I only some of the benchmarks I cannot. There are some testing infrastructure problem. I didn't run all of them. So if you use some aggregation, it's the gen percentage is slightly higher, energy lower. But if that's the thing with some aggregation, it changes your hard-coded value. So if you have some hard-coded values in its scripts that are tuned for max aggregation, if you use some aggregation, you have to change those values. You cannot just use those values. If I tune those values, I can get like almost 40% jank reduction and much less power consumption. I don't want this to be an indicator that some aggregation greatly outperforms max aggregation. That's not what I want to say here. What I want to say is that with some aggregation, because the jank percentage is already pretty low, sometimes in some sub benchmarks it's already single-digit jank frames. So 40% reduction is not that much. I'm just saying with this that if you want to use some aggregation, those hard-coded Uclamp values have to be changed. They have to really tune. Yep, everything. And thank you. I guess any further questions? Okay, yeah.